So this is lecture 9, and in lecture 9, we're going to change course a little bit. So let me begin by explaining the method behind this madness. So the most recent things we have done were in chapter 3. So in chapter 3, we learned how to do proofs where one supposes something and then engages in some strategy, and then at the end of that strategy gets to make an inference. So for example, with conditional proof, where you take on a new assumption, you reason, get a conclusion, and then from that whole argument, infer a conditional. Okay, the next chapter in the book, chapter 4, is called New Proofs from Old. In chapter 4, one doesn't learn actually any new proof rules. One learns how to reason more efficiently with the proof rules we already have. So we're going to skip over chapter 4 today, and we're going to go straight to chapter 5. In one sense, chapter 5 is easier than chapter 4 and chapter 3. And in fact, learning what we have in chapter 5 will help us to do proofs even better. So in short, what you know how to do now is you know how to prove things, but what you don't know how to do is you don't know how to determine whether or not you can prove something. Moreover, so of course, if you prove something, you know that you can prove it. However, if you start to try to prove something and you become frustrated, that's actually not in general very good evidence that the thing can't be proven. It's very unreliable evidence that the thing can't be proven. So we need a better way of seeing when something can't be proven. And that's important for two reasons. On the one hand, so although in this class your instructors give you things to prove, in real life, when you have a job or when you're doing academic research, it's up to you to decide what to prove. So that's a very useful thing to know what's worth trying to prove. However, in this class, it will also be important for you to determine what you can and cannot prove for the following reason. In one sense, every proof is made up of lots of smaller proofs. Every step in a proof is itself a little proof. So when you construct bigger proofs, what you need to know is which sub-strategies. So if you're trying to get from some premises over to a conclusion, you need to know which steps will succeed along the way. So it's very important to be able to check that some moves can't possibly work. Okay, so that's what we'll do today. So in particular, we will talk about using truth tables, which is something that many of you probably have seen before, using truth tables to determine if a sequent is valid, and that means in this case whether it's provable or not. Okay, so I'll give you a quick overview of what will come next. So I'll start with an example and discuss the general strategy. Then I'll go over the details of what the individual truth tables for the connectives are. Then we'll put those individual truth tables together into a general recipe for determining if sequents are valid or not. So now we come to the first example. Okay, consider the following sequent. Premise, either if P then Q or if P then R. Conclusion, if P then Q or R. Is that provable or not? Okay, so maybe you have intuitions already, maybe you don't. But let me say what one would like. So I'm going to try to explain the method behind the truth table before we start getting into the details. So what feature should a valid sequent have? And now we know that it should have the feature of being provable. That's what our system is for. But let's think of it from a different direction. What would be the kind of thing we don't want to prove? We don't want to be able to prove something where the premises could be true while the conclusion is false. So in other words, we want for our proof rules to have the feature that the resulting sequents are truth preserving. So I'll just write that down now so we can remember, because that's a big important phrase for the concept of validity. So we want our sequence to be truth preserving. But what does that mean to be truth preserving? Because there's no truth anywhere in sight here. There's just sequence. There's just proof rules. So what we want to know is if this were true, the first premise, in this case there's just one premise, then the conclusion would be true. Okay, so well, but now we run into another problem. What would it mean to say the premise if it is true? Because it's not true or false, it's symbols. Symbols are not true or false. So if I said something like Princeton is in New Jersey, you say that's true. I say Princeton is in Massachusetts, you say that's false. But if I say if P then Q, is that true? And you say I don't know because I don't know what P is and what Q is. So here's the basic idea behind truth tables. We don't know what P, Q are. The other atomic sentence letters, we don't know whether they're true or false. That's not the business of logic to know whether they're true or false. But we do assume, this is a key assumption, assume first that any atomic sentence can be true or false. Okay, and it must be exactly one of those two. So any atomic sentence is either true or is false. And the second assumption is any two distinct atomic sentences are independent from each other. So in other words, we are assuming that P and Q have no connection between them. So that is the sense in which they are atomic, they're independent. So any combination of truth values, trues and falses to the different sentence letters, any such combination is possible. Okay, so atomic sentences are independent from each other. That's the second assumption. Okay, so given those two assumptions, what that means is we can now form a list of all the possibilities. So let's do that on this page. Okay, so suppose we have atomic sentence P, atomic sentence Q, atomic sentence R. We could have many more. For us, for now, it will be enough to talk about 2 or 3. Okay, now we assume that each one can be true, each one can be false. For simplicity, for notational simplicity, I will use the number 1 for true and the number 0 for false. Okay, so P could be true, 1, or P could be false, 0. Q could be true, 1, Q could be false, 0. R could be true, 1, R could be false, 0. All those possible combinations. Now, for those of you who are into combinatorics and that type of thing, you probably already can figure out how many different combinations are possible, but let's take it a little bit more slowly. So let's just start to list them, and I'll tell you a little trick that will help you remember to list all the possibilities. So we'll start with the possibility where they're all true. Now, here's what we can do is we can quickly look and think, P can be true. Think of all the different ways that Q and R could be while P is true. So let's do that first, and let's start with the cases where P is true. And you'll see fairly quickly, if you just start listing them out, that there are 4 different ways that Q and R could be when P and Q are true. And again, I'll list those systematically. What I'll do is I'll put the 2 cases where Q is true first, and the 2 cases where Q is false second. Now, then we can alternate with R so that these first 4 rows give me all the possibilities where P is true. Now I can just repeat. We have all the same possibilities with Q and R when P is false. Okay, so we have P false, 4 different ways. And then again, we have Q true, Q false, R true, false, R true, false. Okay, so there are In total, as you can see here, again, I said the combinatorialists among you can see that there are 8 quickly, 8 possibilities. That's 2 cubed. And it is true that in general, when you have n atomic sentences, there are 2 to the n possibilities. Okay. So these are all the different possibilities when you have 3 atomic sentences we just listed. Okay, now with that in the back of your heads, remember what we said before, going back to our previous page. We want to talk about if the premise is true, then the conclusion is true. Rephrase that in our minds now. What that says is whenever the premise is true, the conclusion is true. What does that mean? Whenever, it means in all situations, in all possible circumstances. In short, no matter what the value of P, Q, and R are, what they are, when the premise is true, then the conclusion is also true. That's what it means for the argument to be valid. So the next thing we need to do is to figure out what is the truth value? Is it true or false, this premise, when P, depending on the values of P, Q, and R? So this is another basic assumption we now take on. We assume that whether a sentence is true or false depends only on the atomic sentences that occur in it. Then you can calculate whether the sentence is true or false from the atomic sentences. Okay, so I'll put that in as a third assumption. Truth, falsity depends only on atomic sentences and, of course, the way the sentence is put together with the connectives, with and, or, if, then, not. Okay, so this comes to the next bit. I told you that the next thing we have to do is to just tell you how to calculate the truth values of complex sentences from the truth values of their components. Okay, so I'll go on to a new page for this. This is also in the book. So these are the truth tables for the connectives. So I'll just list these very quickly. I'll tell you, as with the proof rules, it doesn't pay much to sit and stare at these and try to memorize them. It's better to look at them while doing problems. Okay, and if you do lots of problems, which of course you should do even more than we require for you in the class. You should practice, you should train yourself. You'll just memorize the truth tables by doing them repeatedly. Okay, so now I'll tell you what those are, starting with our one and only unary connective. So our one and only unary connective, that is a connective that has one input, is the not connective. Okay, so here we have, take the truth value of some sentence, phi, and the truth value then of its negation, not phi. Okay, I'll tell you this quickly, not surprisingly, right? It is the reverse of the truth value. Okay, so the not just flips the truth value. Now pause for just a second, quick philosophical point. Why did I write phi? I wrote phi because phi is not necessarily an atomic sentence. Any sentence, when you know its truth value, then its negation is directly computable from that truth value. It just flips the truth value of the thing. So that applies to anything. So for example, in the case where the truth value of, say, P and Q were true, then not, parentheses, P and Q would be false. Okay, so that's a simple case. Okay, we have 3 other connectives. We'll just do those quickly. So we have and, or, and then if then. I'll do and or very quickly and then spend a little bit of time talking about if then, because that tends to be something that people stumble on a little bit more. Okay, so the and connective, what we have is an input of 2 sentences. So we have, say, phi and psi, and then we're going to compute the truth value of phi and psi. Okay, if there's 2 sentences, there are at most 4 different possibilities for their truth values. Since these are complex sentences, they may not be able to take on all these truth values simultaneously. but the maximum number of possibilities is 4. Okay, and the simple rule for and for the conjunction connective is the only way that phi and psi can be true is if both phi and psi are true. So I'm going to do this a little bit patiently here just so that we keep track of what we're doing. So if these are both true, this is true, but otherwise, when the first one is true and the second one is false, it's false. When the first one is false and the second one is true, it's false. And when both sentences are false, it's false. Okay, let me just quickly remind you now that in red, this red box, these are the truth values of phi and psi. This and is the main connective. So always the main connective of the sentence is the one under which you can see the truth values of that sentence in that situation. Okay. So now also we do or. Phi, psi, phi, or psi. It is in a sense the opposite or the dual of and, that is phi or psi is true if just one of the two is true. One of the two is true, it's enough. Okay, so in the first case where they're both true, it's true. In the second case where the first one is true, the disjunction is true. In the case where the second one is true, the disjunction is true. The only case where the disjunction is false is when both are false. Okay, this does make it clear. The truth table for or that I just wrote makes it clear we're thinking of the inclusive or, not the exclusive or. There are many cases in life, in real life, where we use or to indicate one of the two but not both. But that's just because in English, we really actually have two senses of or. We have an inclusive or, where I'm saying one of the two holds and maybe both. We have an exclusive or where I'm saying only one of the two holds. This, what I've just written, is the truth table for inclusive or, and that's what we're going to use the symbol, this wedge symbol, to indicate. Okay, so we come finally to the truth table for the conditional. If phi, then psi. Okay, now I'll go ahead and issue a philosophical warning here. This is not uncontroversial. In fact, there have been philosophers and logicians who spent their entire careers thinking about, is this okay, the truth table for if then? I'm not at this stage in our course going to get deep into those discussions. This is a philosophy class. Those discussions are good. It's good to reflect on these things. However, we need first to learn how to use one proposal. So one proposal for the if then connective is the following. The rule in short is, and this is a very liberal interpretation of the if then connective, the liberal interpretation is the only way for if phi then psi to be false is if phi is true and psi is false. Otherwise, it's true. Under all circumstances, it's true otherwise. That's a very liberal interpretation. So it's when both are true, it's true. This is the one case, line 2, where it's false. But otherwise, oops, that's a wrong, filled that in the wrong way. Let me go back and rewrite this as 0, 1, it's true, and 0, 0, it's also true. Those last two lines are, in many cases, a bit puzzling, right? So it's a bit puzzling that you could have something, a conditional be true, just because the antecedent is false. So I'll just leave that there, and we'll start to use these. Okay, so So let's look at a concrete example. Okay, we'll start with a very simple example, an example that doesn't even use the connectives. So suppose that you were asked, is this sequent from P infer Q, is that valid? Okay, and what I'll do in this case, so you know the answer obviously is no, it's not valid. And to put that concretely in terms of truth tables, there is a case where the premise is true and the conclusion is false. How do you know that? You know that because we've assumed the premise being an atomic sentence and the conclusion, a different atomic sentence, are independent of each other. So of course P could be true while Q is false. But suppose we want to be a bit more pedantic and write out a full truth table to display that there's a case where the premise is true and the conclusion is false. So I can do that, and I'll do that here. Thank goodness for you, you have a fast forward button, and so you can fast forward me. Okay. Okay, so this is how I can set it up in general, is I have a truth table here. I've put my premise on one column here. So here's my premise, and then here's my conclusion, and then here's my task. My task is there a row where the premise is true and the conclusion is false? If there is, then the sequent is not valid. If there is not such a row, then the sequent is valid. Okay, so in this case, you know how it's going to turn out because we'll just write out the different possibilities. Okay, now this is just a matter of copying over to the right. So 1, 1, 0, 0, 1, 0, 1, 0. Among these different scenarios, is there a case where the premise is true and the conclusion is false? Yes, there is. There is on line row 2. And this is what philosophers call a counterexample. So it's an example that shows that the argument is not valid. It is not truth preserving. Okay. Let's do a more interesting example now. Okay, so let's actually start with something simpler than what we began this lecture with, because the thing is, as soon as you have 3 atomic sentences, you would have a truth table with 8 lines. If you had 4 atomic sentences, you would have a truth table with 16 lines. This quickly becomes unwieldy. So what we're going to do in just a minute is we're going to think of ways one can bypass writing out a full truth table. I will tell you in real life, so as you may have suspected from the way we've talked about this, is truth tables are something that can be automated. You can actually program your computer to compute the truth table for you, or you don't even have to be that diligent. You can actually go to the internet and find that somebody else has already done that. Okay, but again, you need to develop your intuitions and not just, outsource this to the internet. So let's start with a simpler type example. Let's look at the sequent, not if P then Q. Does it follow from this that if P then not Q? Okay, so I'm going to write this out in full. Okay, again, P, Q are our atomic sentences. Always in a full truth table, the columns on the left over here will have all of the atomic sentences that occur in any of the premises or conclusions. So we'll have all of those because you have to consider all the different possibilities. Okay, so then it's just going to be the standard, boilerplate. Always for P and Q, there's 4 possibilities. And now we put in our premise, not if P then Q, and our conclusion if P then not Q. Okay, now what I'll do in this case is the one step I'm going to skip is I'm not going to copy the truth value of P and Q in under, just because it will be hard to see everything's going on. So I'm going to be very careful, and I'm going to compute from the inside out. So in other words, in the first line, I'll be very explicit, and then subsequently I'll be a little bit less explicit. So here, you must start by assigning the truth values to the atomic sentences. That's always the first step. The second step is to build outward. So when you're applying truth values, you start with the atomic bits, then you assign the next thing you can. So for example, in this case that we have in front of us, I can't yet at this stage determine, I can't figure out the value of this not here because I don't have the value of the conditional yet. Okay, so you have to go from the inside out. So in this case, I start with the conditional, and that's true. So remember the truth table for conditional. If P and Q are both true, the conditional is true. Now the truth value for the negation here is false. Okay, so that was working from the inside out. Now on the right-hand side, the conclusion, the negation here comes first. So I can't compute the truth value of the conditional because first I need to compute the truth value of this. Now in this case, the conditional comes out as, oops, that was a mistake. The conditional comes out as false because what it is that's the truth table values we're applying, because in this case, technically what's going on is it's if P then not Q, and that's what we need the truth value of not Q. So the truth value of P here is 1, truth value of not Q is 0, so the conditional if P then not Q is 0. Okay, so that's how we proceed. Now I'm just going to start to build up more of these. And notice, by the way, this first line is not a counterexample because the premise is false. So the premise, not if P then Q on the first line, first row, is false. So it's not a counterexample. The only case for a counterexample is where premises are true and conclusion is false. That's not a case we have here. So let's proceed now. Okay, in the second case, P is true, Q is false, which means that the conditional is false and its negation is true. Okay, P is true, Q is false. Not Q is true, so if P then not Q is true. Okay, in the second row, the premise is true and the conclusion is true. So it's not a counterexample. So actually, information-wise, it doesn't tell us anything yet. We have to keep going. Okay, next line, P is false, Q is true. That makes the conditional true, and it makes the negation of the conditional false. Now notice, by the way, if your goal is to figure out is this sequent valid or not, already you know the premise is false on this line, this row, so this row is not useful for checking if it's valid or not. However, I'll just go ahead and compute the conclusion in this case. It's P is false, Q is false, which makes not Q true, so the conditional here is true. But again, this is not helpful for us. Finally, we go to the last line. P and Q are both false, makes the conditional true, makes the negation of the conditional false. Okay, so once again, we have false premise. So this row can't be a counterexample to the validity of the argument, but I'll compute the conclusion as well. So the conclusion, P is false, Q is true, so this is true. So what we have here now is none of the four possibilities is a possibility where the premise is true and the conclusion is false. None of them happen. None of that happens in no circumstance. So the argument is truth preserving. It's valid. And then here's my promise to you. If an argument is truth preserving, it can be proven. It is valid. It can be proven. You have to take that on faith right now. You have no guarantee in the form of mathematical proof, but that is how our system is designed. So in this case, the conclusion will be provable from the premises, from the premise. Now, I will give you a quick hint about this particular one. In this particular case, from not if P then Q, it's pretty easy to see that not Q follows. So you actually have just learned recently reductio ad absurdum. If you assume Q after assuming the premise, you can derive if P then Q. That's positive paradox. And so therefore you have a contradiction with the premise. So you can see that you can prove not Q, so therefore you can prove if P then not Q. Okay, so in short, this argument you can show by the truth table method that it's valid, and I've just given you a quick hint about how you can prove it. Okay, let's go back now to the very first thing we started with. Let's go back to this argument here. So if P then Q, or if P then R, then does it follow that if P then Q or R? Okay, so now what I want to tell you is there's a way you can do truth tables without actually writing out a full truth table. And so that's what I want to explain to you right now. Okay, so we want to see if there is a case where the premises of this argument, or the premise of this argument, is true and the conclusion is false. If we did this longhand, if we wrote this out in full, we would have a truth table with 8 rows. So it would be quite a lot of writing in ones and zeros and making sure we had everything in order. Notice, however, that it's enough. We actually can ignore all the rows where the conclusion is not false. So if the conclusion is true, that supplies no information about whether the argument is valid. The only way it could fail to be valid is if there's a case where the conclusion is false and the premise is true. So let's actually focus in on the case where the conclusion is false. So if that were 0 in this case, then ask ourselves, could the premise be true in that case? Okay, in this particular case, the conclusion being false is very restrictive because the conclusion is a conditional, and so the only way it can be false is if the antecedent is true and the consequent is false. What's more, because the consequent here is a disjunction, the only way it can be false is if both Q and R are false. Okay, so notice I've gone from the hypothesis that the conclusion is false to determining the truth values in this case of P, Q, and R, and that's going to determine the truth values of the premise. So I'll just go fill those in. I have P true, Q and R false. So both of these conditionals are false. So this disjunction is false. So the only way for this conclusion to be false is if also the premise is false. So there's no way for this argument to have true premises, no case where it has a true premise and a false conclusion. So it's valid. Okay, so I just used reasoning to figure out that there is no row in the truth table, the 8-row long truth table. There is no row where the premise is true and the conclusion is false. Okay, so in summary, what we've learned is that the way to check whether an argument is valid or not is you check whether there's a case, a scenario where its premises are true and the conclusion is false. What we mean by scenario or case is an assignment of truth values, 0s and 1s, to all the atomic sentences, which are taken to be independent of each other. Then to compute all the values of the sentences in the scenarios, you work from the inside out. That is, you start by assigning truth values to the atomic sentences and then computing the truth values of the sentences built out of those until you get to the truth value of the main connective of the premises and the main connective of the conclusion. And then in theory, you inspect all those and see, is there a counterexample? In practice, you can save yourself some time by thinking and asking yourself, is there a case where the premises are true and the conclusion is false? And then using some heuristics to look to search for the possibility like that.